we're now going to start thinking about what happens when we, excuse me. We've been talking about probabilities of events. We've been talking about random variables, in particular random variables that come from drawing tickets out of a box at random and looking at the numbers on the tickets that we get. And we want to start looking at what long-run regularities there are in order to be able to use these box models to draw inferences about the world. One of the most fundamental notions that's applied to random variables is the expected value. And this chapter is about that, but in order to get there, I want to talk about the law of large numbers, which is a key concept in probability. So let me write this with chalk because it's easier to talk it through. So let's suppose that we have independent trials that have the same probability of success. So we can imagine tossing a coin repeatedly, really vigorously, in such a way that whether the coin landed heads each time is independent of the other times that we toss the coin. Okay? So n is the number of times I toss the coin. And p, if the coin is fair, we're sort of by definition, what we mean is the chance that the coin lands heads is 50%. Okay? Now, suppose we look at the difference between the number of heads. Boy, that's really illegible. Okay, so this is the number of heads we get in this many independent tosses of the coin. Okay, so this is a random variable. The number of heads you get in a certain number of tosses is random. Okay, so this ratio is random. It depends on what actually happens. And suppose we look at the difference between that and 50%, which is the probability that the coin lands heads in a single toss. By definition, we're talking about a fair coin. So this is kind of rarely going to be exactly equal to 50%. Yes? Just every once in a while it might happen. But what tends to happen is that let's look at the difference between the empirical fraction of successes, the empirical fraction of heads, and the probability of success, the probability of heads. And let's look at, so this thing could be big, it could be small, right? Could so happen that the fraction of heads in 17 tosses is 90%. And so 90% minus 50% is a big number. It's 40%, right? It could happen that this is really small. It could happen that the fraction of heads in 20 tosses is exactly 50%. This number is 0. All right? So this difference is random. Right? It depends on what this is, and this is random. Right? Let's ask, though, what's the chance that this difference is less than some positive number epsilon? So we're going to look at the probability that the difference between the fraction of successes and the theoretical probability of success is less than epsilon. And the law of large numbers says that this probability goes to 1 as the number of tosses goes to infinity. So the more trials you have, the more likely it is that the fraction of successes you see is arbitrarily close to the probability of success. Okay, so this is true for any fixed positive number epsilon. So we have some epsilon greater than 0. So for any fixed epsilon greater than 0, the chance that the theoretical probability differs from the empirical fraction of successes by less than that threshold value epsilon gets bigger and bigger and bigger the more trials you have. Okay, this is the law of large numbers. Right. Everybody remembers what a limit is? Yep. Okay. So this is a funny notion of a limit because it's a limit of a probability. It's still possible that the fraction of successes differs from the probability of success by more than epsilon. Right? It can still happen that you toss a coin 1,000,000 times, you get heads 1,000,000 times. It's just very, very, very unlikely. Yep. Okay, so the chance that these things differ by very much gets really, really small the more trials you have. The chance that the difference is really small gets big the more trials you have. You have independent trials, same probability P of success in each trial.